Welcome. In this lecture, we shall consider solving a cantilever beam problem consisting of multiple loads using Macaulay's method. We in particular shall specifically highlight the care that needs to be taken for identifying the reference coordinate system with respect to the type of the beam and the orientation of the triangular or the uniformly varying load. We shall also look into the considerations to be taken to express the external moment at some arbitrary location along the length using Macaulay's singularity or half-range functions, and finally, the expression for the uniformly distributed load, particularly when it is not acting on the entire length of the beam. Let us draw the given cantilever beam with the lengths of various parts and the load values. The area moment of inertia is equal to 1 times 10 to the power of 9 in millimeter to the power of 4 units. The Young's modulus of elasticity is equal to 2 times 10 to the power of 5 megapascals. We begin the solution by first deciding the location and orientation of the reference coordinate system, from where the distance of the arbitrary cross-section shall be measured. Looking at only the type of the beam, it has been already discussed earlier that it is convenient to consider the reference coordinate system at the free end of the cantilever beam, since the beam reactions may not be required to be found out. Apart from this, we need to look at the way the uniformly varying or the triangular load is placed on the beam. If the coordinate system is taken at the fixed support for the given beam from where the distance x of the arbitrary cross-section is measured, then this would necessitate writing two load terms for the triangular load, and hence they shall act two bending moments at the section created on account of the imaginary section in region EB. We may need to write the moment due to a part of the load which is of the uniformly distributed load type, and the moment due to the other part which is again a triangular load type, making the process cumbersome, lengthy, and confusing. We therefore prefer to show the reference coordinate system on the extreme side of the beam where the apex of the triangular load is pointing. This would necessitate writing only one term for the load and hence the bending moment at the imaginary section. For the given problem, hence, we prefer the free end of the cantilever beam, that is point A, as the reference end. The coordinate system is drawn with deflection y taken positive in upward direction and distance of imaginary cross-section taken positive when pointing towards the right. We now write the differential equation of the elastic curve in the form of the bending moment. That is, m at x equals ei times d2y over dx square. This is equal to the summation of moments of resistance acting at an arbitrary section by each load and moment. In effect, we try to apply the principle of superposition here. Specifically, if the assumed cross-section is in the region AC, then the moment is given by minus 5 kN per meter times x meters, that is the equivalent point load, times a half of x. This term is left undisturbed once written and is valid even though the assumed cross-section crosses to the right beyond point C, where the uniformly distributed load is supposed to actually end. To nullify or remove this imaginary extra uniformly distributed load added to the beam to the right beyond point C by retaining the moment term, an equal amount of imaginary uniformly distributed load added beyond point C is now added and acting upwards, and this term is also retained till the imaginary section is reached at the end of the beam, that is at point B. The moment due to the imaginary upward uniformly distributed load acting beyond point C is given by the term plus 5 kN per meter times x minus 2 meters times a half of x minus 2. Note that all the arguments containing the variable x are enclosed in pointed brackets as our notation to describe the half-range functions defined earlier. Now, the third term is written for the bending moment of 10 kN meter at point D at a distance of 3 meters from point A. It may be tempting to express the bending moment simply as plus 10 kN meter as the third term in the bending moment equation. But this is the wrong notation. You might wonder why. Later, once we integrate this equation once and twice to get 10x and 10x square over 2 respectively for slope and deflection equations, and then happen to find the unknown constants, this third term will be retained when we need to estimate either the slope or the deflection in the regions to the left of point D. Actually, for slope and deflection calculations for the regions to the left of point D, The contribution of the third term, that is from the acting moment of 10 kilonewton meter, should not be considered as such, and the representation of the third term simply by 10 kilonewton meter in the moment equation does not allow us to cancel this term using Macaulay's notation. The solution to this is to represent the third term not by simply 10 kilonewton meter, but by 10 times x minus 3 to the power of 0 in pointed brackets. Note that x minus 3 to the power of 0 is equal to 1, as anything to the power of 0 is 1, and this does not affect the third term at all, and it retains the moment units of kilonewton meter as well. What effect this x minus 3 to the power of 0 does when multiplied with 10 kilonewton meter in the bending moment equation is that it gets converted to 10 times x minus 3 to the power of 1 and 10 times x minus 3 to the power of 2 over 2 in the slope and deflection equations respectively when integrated once and twice. Now, this feature shall enable us to cancel out the third term when not necessary, that is, when it is required to estimate either the slope or deflection at cross sections to the left of point D. The argument in pointed brackets x minus 3 becomes negative and hence taken 0 and gets automatically deleted. The 3 in the argument x minus 3 actually enables us to know where exactly the acting moment is placed in the beam along the length, and by using the Macaulay's notation we can either delete it when regions to the left of acting moment are analyzed, or consider it when the regions to the right of the acting moment are analyzed, where the argument becomes positive. For representing the fourth term of the bending moment equation corresponding to the uniformly varying or the triangular load, we have half times x minus 4 times the height of the triangle at distance x from the reference from where the imaginary cross section acts to get the equivalent point load acting at the center of the triangle times the distance from the section so as to get the moment term. The ordinate or the height of the triangular load at distance x from the reference can be found from simple interpolation as 10 times x minus 4 kilonewton per meter. We can have a check of the correctness of this formula. Let x equal 4. This corresponds to the point E where the ordinate E is calculated as 0. Also, let x now equal 6 corresponding to the point B. Here, the height is calculated as 20 kilonewton per meter and it is in fact the maximum value of the ordinate from the given data. The moment created at the section from the equivalent point load acting at the center of the triangular area can be hence written as half times the base, that is x minus 4, times the height, that is 10 times x minus 4, times the distance of the centroid from the section, that is a third of x minus 4. The terms in the bending moment equation are integrated once and twice. The boundary conditions are introduced, namely the slope at the fixed end equals 0 and the deflection at the fixed end also equals 0. We therefore get the values of the unknown constants as C1 equal to 103.33 and C2 equal to minus 445.66. We substitute these values back to get the final slope and deflection equations. Now we can find the slope and deflection at any cross section along the beam length in radians and in meters respectively. For the free end of the beam, that is for x equal to 0, the deflection is calculated to be minus 0.00222 meters, that is 2.22 millimeters. Minus sign indicates that the deflection is acting downwards as against the positive sign of the coordinate system acting upwards. In the next lecture, we shall solve another problem of a beam with multiple loadings for slope and deflection using Macaulay's method.